So when we look at our problem like this, it says if 50 grams of silicon dioxide is heated, then 27.9 grams of silicon carbide, SiC, is produced. What is the theoretical yield of silicon carbide, and then what is the percent yield for this reaction? So one thing I want us to do in the problem itself, I want us to label what is a product and what's a reactant up in that first sentence in the story problem. So it mentions 50 grams of silicon dioxide, SiO2. Looking at that equation, is SiO2 a reactant or is SiO2 a product? That's a reactant. So I'm just maybe going to put the word reactant either on top of it or down below it, so I'll know that has to do with an amount of a reactant. That means I'm not going to use 50 grams itself in the percent yield equation. 50 grams of silicon dioxide is neither an actual yield nor is it a theoretical yield. It's an amount of a reactant. Cade, let me get you to put your computer. Caden, let me get you to put that away. Thank you. Then we've got 27.9 grams of silicon carbide. Now that's actually a product. It turns out that is what I would consider my actual yield. That's how much they actually produced when they did this experiment. So that's my actual yield that I'll eventually use for part B. But first I need to find a theoretical yield in part A. To find your theoretical yield, you're going to do mass-to-mass stoichiometry starting with 50 grams of silicon dioxide. So I'm going to say given 50 grams of silicon dioxide, SiO2. And then I want to find out how much silicon carbide, SiC, say grams of silicon carbide that I would expect to get. This is going to be called the theoretical yield because it's going to be based on mass-to-mass stoichiometry that I'm going to get from this reaction. So just like the bell ringer, I'm going to do some 3 steps of stoichiometry here to go from 50 grams of SiO2, change it to moles, use the mole ratio, and then convert it into grams to see how much I should get here. So the theoretical yield is where you take your reactant and you do stoichiometry to get that same product. All right, so in my steps here, step 1, I need to divide by that molar mass basically. So I'll get that molar mass of silicon dioxide. You go ahead and put the molar mass of SiO2 while I try to get the TV back up and running. We'll go to the 100th place here. I got 60.09. That's about 0.832. I need to keep at least 3 sig figs. I might keep a 4th. And actually, I'll just keep all the digits in my calculator, so my calculator will have all the digits. Now, this substance is still the SiO2. Because in step 1, I just changed it to moles, but it's the same thing. Then I'm going to go back up. I can tell this reaction's balanced because they already gave me a couple of coefficients, so I can assume it's balanced. If I have 0.8321, I'm going to put that underneath silicon dioxide there. What's the mole ratio of silicon dioxide to silicon carbide. Yeah, it's 1 to 1. So I divide by 1 times 1, or just realize that's the same thing. So I divided by 1, multiply times 1. And then I want to get that into grams for my final step. So I'm just going to call that step 2 up there. And then finally, I want to convert that 8321 moles of silicon carbide I'm all out of room here, huh? Gonna have to take it down here. I'm going to convert that into grams. I would do this on the same line, but I'm trying to fit this all on the screen here. So I'll find the molar mass of silicon carbide. 28.09 plus carbon is 12.01. 40.10 grams, my final molar mass. Okay, so I'm going to write that on the whiteboard, how it's a little bit neater, how I would like to write it if I had to. That's how I would like for that to look, so we can see the reading I do it, so it almost cancels there. Alright, so I'm getting 33.37. Go with 33.4. That'll keep my 3 sig figs that I needed. All right, that is called the theoretical yield. That means if every last molecule of silicon dioxide reacted, I would get 33.4 grams of silicon carbide. It's based on math, it's based on the stoichiometry. So I used the reactant from the chemical reaction, and I did stoichiometry with it to get the amount of that same product that they mentioned in the story problem also, to get the theoretical yield. Percent yield is going to be easy now. Percent yield is just where we divide the actual over the theoretical. That gives us a decimal, and we want to change it to a percentage for our final answer. So, percent yield all right, it's the actual amount. It says in the story problem, how much did they actually produce? 27.9 grams. How much were they expecting to get based on the stoichiometry? 33.4 grams. And then you just take that and you multiply it times 100 and put a percent sign on it to turn it into a percent yield. So part B is easy. Part A is where we got to do all the work. 27.9 divided by 33.4. I'm getting 0.835. Just put 0.835, I'll take a point off. All right, it needs to be 83.5%. That's what we mean by percent yield. And the only unit here is just percent. You don't have to worry about SIC or anything like that. It's just the percentage based on how much you expected to get compared to how much you actually got. So raise your hand if you have any questions there. When people do these on their own, the most common thing that they kind of takes them a minute to figure out is, which one do I start with for the stoichiometry? For my theoretical yield, I had to start by picking out the reactant and then converting the reactant with stoichiometry into grams of that particular product that they mentioned. Well, there's 2 products here. The other one is CO. I don't really care about how much CO I made because in the question they never mentioned CO. The product that's mentioned in the question is the silicon carbide. Anybody have any questions there? All right, I got one more sample problem to talk a little bit more about why percent yield might be useful. Try to find that same slide that you have on your paper. All right, so this one's slightly different in the way it's worded and kind of the way that you solve it. The first step is still going to be the same, where we're going to do some stoichiometry to find our theoretical yield. But then they actually give us a percent yield and we have to use it for something. So it says, what is my actual yield of uranium hexabromide if I start with 100 grams of uranium and I know that this reaction has a percent yield of 83%. So once again, I want to identify what's given to me here. It says 100 grams of uranium. And I tell you what, I'm going to cheat a little bit. I'm going to add a decimal there. Just it'll be a lot easier to follow this one if we can keep up with at least 3 sig figs. If we round everything to 1 sig fig, it may not make a lot of sense. So let's say 100 grams of uranium. Is uranium a reactant or is uranium a product for that given chemical reaction? That's a reactant, yeah. So I'm going to just mention that here. That's a reactant. That means that 100 is probably not going to be used in the percent yield equation. The product that they're talking about in this one is the only product here. Uranium hexabromide, that's my product that we're worried about. All right, well, let's go ahead and find the theoretical yield first. The theoretical yield is the one that's going to use the stoichiometry. So let's go from 100 grams of uranium. Let's convert that into, eventually, let's convert it into grams of UBr6. It says a 6 there. All right, so we'll go through those steps again. 100 grams of uranium. Let's convert it into moles. Uranium has a big molar mass. 238.03. So 100 over 238.03. It's going to be about 0.420. I'll keep at least 3 sig figs. I like a safety digit, so I'm going to keep a 4th one there. All right, what's the mole ratio of uranium and UBr6 in this chemical reaction? Yeah, it's 1 to 1 again, huh? So I'll divide by 1, multiply times 1, or just realize, oh, that's the same number. But if they weren't ones, we might want to do our calculation there to be sure of it. But we know that's it. All right, and then we'll do our last step of the stoichiometry process. We'll go from moles to grams. That was moles there. We've seen yet. Again, you can't have too many sig figs at this point, so I just accidentally went to the hundredths place because it's my habit. That's fine. It's not my final answer, so more sig figs is better until your final answer. This is what we call, again, this is the theoretical yield. If this reaction were to go to 100% yield, we would expect to get all 301 grams of UBr6. But this percent yield is not 100%, it's only 83%. So we should only get 83% of 301.39. Whenever you say of in a sentence in math language, that's times. So 83% of 301.39 is 83% times 301.39. So that's how I'll finish this one up here. Times 83% means that my actual yield, so again, this time I'm trying to solve this for the actual yield. Just write that word there. About 250, that's going to give me my 3 sig figs. 250 grams of UBr6, that's my actual yield. Most problems want us to find the percent yield, but it kind of shows us why this might be important. If this engineer figured out that the best thing to get for this reaction was 83%, they could use something like this to figure out what they would expect to get from this chemical reaction based on the procedure that they had come up with, if they realized that this procedure only gave them an 83% yield. Anybody have any questions about either one of those? These take a while to do because you've got all your stoichiometry steps and then you've got the percent yield step on top of that. So I've only posted a handful of these. Like some before, I posted these on Canvas for you. So there's an image file on Canvas, but I'll also put it up on the screen if you'd rather just get it off on the screen. And I want you to do these on notebook paper.